Okay, so remember last time I showed you the Rsk algorithm, which takes a permutation and gives two standard tableau of the same shape. So I wanted to show you how to use that on Sage. So, so if you define a permutation, object like this, pi is permutation of 312, then it has an inbuilt method called Robinson-Shenstedt, which will give you a pair of tableau as a list of lists, and it will also give you the corresponding partition because both have the same shape. Uh, so you can ask for the partition. I mean, you could get it from the shape, but it's useful to have some redundancy. So so La is the partition, the Robinson-Shenstedt partition corresponding to pi. So we can repeat the example from the class yesterday. So or last time. So it's 4273615. So let's do that. So 4273615, and if I so let me call this RS. So RS, oops, RS of 0. Separated something. RS of 0 is this. And if I do, so this is the insertion tableau 1352647, and that's what we get. And similarly, I can do RS of 1, which is 1352467. So that is what it is. And somebody asked the question yesterday, what if I take the inverse of pi? So pi inverse is 6241753. This you can easily verify. And so maybe I should call it pi inv. And if I do RS inv equals pi inv dot Robinson-Shenstedt, then I can see that its insertion tableau, so remember indexing starts with 1, is the same as the recording tableau of pi. And if I go 1, then I will see 1352647, which was the same as the insertion tableau of pi. Right. So this is a highly non-trivial fact about the Robinson-Shenstedt correspondence or the Rsk algorithm, which is that if you invert the permutation, the insertion and recording tableau switch. So this is not at all obvious, but it is true. So any questions about this? Okay. So if not, let me move on. So so now I want to remember I'm trying to prove the generating function that advertised at the beginning of the last class. I want to prove this theorem, so I'm moving towards that. So let me I'll prove something more general. So to motivate that, I will recall a quick application. So a corollary of the partition generating function. So let Ps of n be the cardinality of all lambda partitions of n, such that lambda has at most s parts. And so then the claim is sigma n greater than equal to 0, Ps of n q to the n is the product k corresponding to s 1 by 1 minus k. So why is this a corollary? So this is we call Ps of n for s a subset of natural numbers. What this so this is small s. So for this we had this generating function where this k ran over all s for this capital S, and for small s, what this is saying is that I have a generating function. If I write it in if I write its Young diagram, what it's saying is that it has at most s parts. So so there could be a few zeros here, but this has at most s parts. And the idea, I mean, why this is a corollary of that result is that if I take the conjugate for such a lambda, if I take its conjugate, then each part lambda prime has parts in 1 up to s, of course including 0. So then this capital S is 1 through s, and then this generating function pops out, and this is clearly a bijective constant. So then the result. The generating function of S. Is that clear? So it's not, I mean, it's not maybe immediate, but it's an easy consequence once you have the Young diagram. Okay, so what we're going to do is I mean, we will prove this result, but we will prove this a more refined result from which this will pop out as a corollary, which will generalize this result. Okay, so we are going to move towards that, and before okay, so before I go there, so let me quickly remind you that we have two kinds of objects. One are these standard Young tableau, which are fillings from 1 through n of the Young diagram, which are increasing as you go along rows and as you go down columns. And on the other hand, you have plain partitions, which are like this example over here, which are, if I write it in an array form, these are decreasing weakly as you go to the right and as you go down. So they're not the same thing, but they are sort of related. Okay, so the inequalities for standard Young tableau and plain partitions are different. Okay, so I want you to keep that. Okay, so now I want to define what is going to be important for us. A column strict plain partition which I want to call it CSPP, but CSPP stands for Cyclically Symmetric Plain Partition, so I'll use CoSPP is a plain partition for which non-zero entries decrease strictly along columns. So the name tells you what it is. So it's strict along columns. So remember I talked about strict partitions. Oh no, well, I talked about distinct partitions, which are also called strict partition. So the strictness is only along columns. So now we are breaking the symmetry. So for example, there were 6 partitions of the 6 plain partitions of 3, but if you look at the column strict plain partitions of 3, you only have 4 of them. So 3, let me not put parentheses. 3, you have 2, 1, you have 2, 1, and you have 1, 1. So it's allowed to, equality is allowed in rows but not in columns. So the 2 which we are missing are all containing 1. So 1, 1, 1, which fails the decrease. 1, 1, 1 fails, and of course 1, 1, 1 fails. Okay, and the shape of a column strict plain partition, or of a plain partition in general, is the partition whose Young diagram it is a filling off, and it's denoted P. This is denoted SH. Okay. So, for example, in the above example, the shapes are, so for 3 we have just 1, the partition, singleton partition 1. This is the partition 2, singleton partition 2. This is 1, 1, and this is 3. Okay. Any questions about this? Okay. So, since I said I want to make programming somewhat part of the course, so let us write a program to check if a partition is a column strict. So So here is my set of plain partitions. I'm taking a random element. Here it is. And here is what it looks like. So this is 333, 331, 211. And okay, so this program I had already. So as I said, Sage sort of uses CoSPP to check if something is a cyclically symmetric plain partition. So I don't want that. So, and Sage does not have anything to check if something is a column strict plain partition. So this is something that one has to write. So let me sort of show you how to write it. So it is good to keep playing around with a dummy example just to make sure there are no problems. So, and to know what methods one. So, if can I do p of length? No, I can't do p of. Can I do p dot size? No, I can't do. So, what about len of p? So remember, p is this example. Okay, so let me erase this. I don't need this. So p is this example. So P has 3 rows. Okay, so let me say n is len of P, and now I want to see how many columns it is. Okay, so maybe this is not good. So maybe I'll do 3, 4, 2, so that everybody is different. So P has 3 rows, but it has 4 columns. Okay, so now I do m equals P of 0. So here I am assuming that I mean, it is padded with zeros at the end. So in general, if it is not, so for example, if this partition were 2, 2, 2, 2, 1, 1, 2, 1, then my program will run into trouble. So maybe you should, or actually, let me not do this. Okay, so let me write it without this assumption. Okay, so for okay, so how should I do this? So I want to check if it's column strict. So if at any point of time I get that it is not column strict, then it should return false. So how should I do this? So for I in range n, so if okay, so for j in range len of p of I, right? So I'm looking at the length of p of I. So I goes from 0 to 2 because remember Sage convention. So here it will go from so the one thing I have to do is I have to go one less because I'm going to compare with the row below. So and then I'm going to go for each row, I'm going to go all the way to this. And again, this will run into trouble, but okay. Now, so if P of I j is equal to P of I plus 1 j, right? If at any point of time this there's an equality, I mean I'm assuming already that P is a plain partition. Okay, so I'm not checking if it's a plain partition, even though if I was really being a good programmer, I would check. So here I return false if at any point of time this happens. Otherwise, I return true. Okay, so this should not be a problem. Okay, so and I've also added comments. So for comments, it's good to put 3 inverted commas. It's good to enclose the comments with 3 inverted commas, and it's in general a good policy to comment, because when you write many programs, then you will tend to lose track of what a particular program is doing. Okay, so I shouldn't have capitalized it. Okay, so here it is. So column strict plain partition. Now let's check if our fellow is. So already once you define a function, you can see that Sage knows about it, so you can use tab completion. So is our example column strict plain partition? Well, clearly not, because for example 2 repeats. So you see this program is going to give me an error. Okay, so okay, so can anyone spot the mistake in the program?
Sir, I think like if there's zeros, the padding in zeros, that will come as an issue, right?
Yes, exactly. So the definition was non-zero entries. So in my sloppy program, I did not check. Okay, so let's do this thing. So let's use my stupid program, and I think we will find. So P is the set of all these plain partitions. So let me check if I get any plain partitions here. So I get only one, which is when all are distinct. You see, this is the problem. So how do I rectify it? Okay, so good. So I made some mistake. So what I want to check is that Pij should not be equal to 0. Because if it is, then the guy below it will also be 0, and then there is nothing to check. I mean, then I should not be checking, because I should only check for non-zero entries. Okay, so let's see. Yeah. So now I get a whole bunch of them, because it's not checking for 0 entries. Right? So there are many of them, and you can check. Okay, so this is an example of a fairly simple program. So next Tuesday I'll have another programming assignment, and I mean it'll be of this level of difficulty. Okay, so please practice these things. Oh, and I wanted to. Maybe I'll stop recording. Okay, that's fine. So I'll add this question in the chat. So let me stop sharing for a second. So I want to add this question. So I want to know how many of you have Sage locally. So please answer this question in this form. Okay. So I have posted this question whether you have installed Sage or not. So I would like to know if you have. That will help lower the burden on CoCalc. So yeah, so let me start sharing again. Unfortunately, this bit is going to be recorded. Okay, good. So now we have a handle on column strip plain partitions. So what we are going to do now is we are going to do an RSK-like algorithm for column strip plain partitions. So it's the difference. So there are two differences. So let's go back to the RSK algorithm for standard. So when we inserted earlier, okay, so let me go to the row insertion algorithm. So when we inserted an element in a standard Young tableau, the rows were increasing and they were all distinct entries. Right? So here they are weakly decreasing and you have potentially repeated entries. So we will define a new row insertion algorithm. So for CSPPs. So given a CSPP K, no sorry, P which is Pij, and an integer K, the CoSPP, I'll use the same notation. The CoSPP P add K is constructed as follows. Okay, step 1. So let R be the smallest integer. So this has the same flavor as the original RSK algorithm, but of course there are certain changes such that K is greater than P1R. So let's compare with here. So here it was the smallest integer such that K is strictly less than P1R. So this is saying that when I look at the first row of the plain partition, I find the largest entry smaller than K. Okay? If no such R exists, as before, add K or append to the first row and define it to be P add K, and then we are done. Otherwise, replace K prime, which is P1R by K, and then again called bumping. It's the bumping algorithm. And row insert K prime into the second row. In the same way. And now continue this way. So this is exactly as before. So continue this way until an element is added as the last entry in its possibly empty row. Okay, so this is exactly the same as before. So let's do an example. So here is my P. So what is it? 774 3331 4331 3221. So this is my P, and now let me insert 6. Okay, so what am I going to do? So what happens to 6 here? So I look at the largest entry smaller than 6 in the first row. So that's 4. So I'm going to bump the 4 by a 6. 3, 3, 3. Now 4 goes below. Now you see the interesting thing that's going to happen. So potentially 4 could have bumped this 4. I mean, when I say that, I mean we had a choice, because now we have repeated entries. So, but what the algorithm tells us to do is to bump the largest entry strictly smaller than it. If this were greater than or equal to here, then I would be replacing this 4. That's not being done. So 4, 4, 3, 1, and now this 3 bumps the 2 in the next row. So this is now 3, and then this 2 bumps this 1 in the next row, and this 1 that's over here, there's no entry strictly smaller than it, so it goes and adds itself over here. Okay, so this is the insertion path. Is the algorithm clear? Okay, very good. So now we want to talk about an analog of Rsk algorithm. So as you can imagine, we are going to have pairs of CSPPs on the right hand side, but what do we have on the left hand side? So we now define an analog of the Rsk algorithm, which we will call Rsk prime. Instead of permutations, now we have rectangular matrices with non-negative integer entries. Okay, so we'll take some R and S, and so example, R equals 3, which is the row number, S equals 4, and R by S matrix, say A. This will be the running example for algorithm. So 0, 1, 0, 2, 1, 1, 1, 0, and 2, 1, 0. Okay. So the space is where we are going to apply our Rsk prime algorithm is going to be the set of R by S, set fixed R and fixed S, and we are going to look at R by S matrices within non-negative integer. But in this form, this is not going to be so convenient to use. So so every such matrix has a unique, sorry, this is my running example, has a unique two-line representation U1 V1, U2 V2, etc. N so that, or rather, it satisfies what are the conditions? Well, U1 is greater than or equal to U2 is greater than or equal to UN. If I is less than J and Ui is equal to Uj, then Vi is greater than Vj, and the number of columns which are equal to I comma j is Aij. A equals Aij. Okay, so this is a non-negative integer, so this makes sense. So let's do this example. So what we are saying is that we will have one entry which is 1, 2, two entries which are 1, 4, etc., etc. Like so. So in the row, I mean in the top row, you want to have the row entries. So and we have to go in decreasing, weekly decreasing. So this A corresponds to the following two-line array. So let me look here. So we will have 3 in the top row 3 times, because okay, let me just write. I think I'm just confusing. 3 2 3 1 3 1 2 3 2 2 1 1 4 1 4. So look at the definition. So the row is weakly decreasing. The top row, I mean, is weakly decreasing. The bottom row is also weakly decreasing whenever 2 entries are in the top row equal. So here is 3 3, there is 1 1. Here 2 2 2, so we are decreasing. Here 1 1 1. So and how many times does 3 2 appear? Well, it is 1, because the 3 2 entry of A is 1. How many times does 3 1 appear? It appears twice, because the 3 1th entry of A is 2, like that. Okay. Any questions about this?
Okay. Can you explain it again? What UJ and VJ correspond to?
Sorry.
What VJ and UJ correspond to? I didn't get that.
So uj corresponds to the row index and vj corresponds to the column. So that's why I comma j. So if let's say uk is I and vk is j, that means that the ijth entry of A is non-zero. Okay, so that's what this means. So unfortunately, maybe I can slightly minimize the zoom. Maybe a little more. So let's look at this. So 3, 2 over here means this is the this one. So this is the 3, 2th entry of A. Clear? Aradhya, is that okay?
Yes.
So look at the second row, for example. So the second row here corresponds to the 2 in the top row, and there is one entry for the third column, one entry for the second column, one entry for the first column. And because of our convention, they are arranged in decreasing weekly. So it's a coincidence for this example that there are same number of 3s, same number of 2s, and same number of 1s. In general, of course. And this capital N is the total sum of A. I mean, how many? If I sum all the entries of A, that's going to be capital N. That's going to be the number of entries in this two-line. Okay, so here is the Rsk prime algorithm. Okay, so just like before, inductively construct pairs of CoSPPs of the same shape. P naught, Q naught, P1, Q1, etc. Pn, Qn, capital N, where this N is the same as this N. Okay, as follows. 1. So start again with P naught equals Q naught is empty. The empty in partition, which is of course column strict practically. At the ith stage, set Pi to be Pi minus 1, insert Vi, the bottom row entry. So we will insert the bottom row of the two-line representation systematically, and add Ui to Qi minus 1, so that shape of Pi equals shape. So let us compare with the old Rsk algorithm. So again, we started with the empty tableau and we inserted pi I, and then we added I to Qi minus 1. So if you think about it, if I write a permutation in two-line representation, of course one has to, I mean the order is all messed up and so on, but if you write it in the usual two-line representation, this is similar to what we do, because in the two-line representation of a permutation, remember I said this a couple of weeks ago, the ith entry is I. So Ui is I, and that's what one is inserting there. Okay, so there's a lot of similarities between this. Okay, so again, let's do this construction for this example A. Okay, so let me copy this. Where it inserted it. So this is my two-line representation. So now let's construct P. So PI, so let's do it like before. We follow the same convention. So I, PI, QI, and I, PI, QI. And as I this shape. Okay, so at the 0th stage, P naught is empty, Q naught is empty, Q naught is empty. The first stage, I'm going to insert 2. Remember, insertion is at the lower level. So I'm going to insert 2, nothing to do, and I'm going to add 3, the top row. And so my partition is 1. The second stage, now I'm going to insert 3. I'm going to insert 1. But there's nothing smaller than it, so I get 2, 1. And then I get 3, 3. Okay, and then the partition is 2. Stop me at any time if okay, now I'm going to insert a 1. Again, there's nothing smaller than a 1, so I get 2, 1, 1. And now I insert 3 in that position. So this is 3, 3, 3. And my shape is 3. Okay, now I'm going to insert this 3. There's of course many things smaller than 3. The largest thing smaller than 3 is the 2, so it bumps the 2. So I add this, and then the 2 goes down. There's nothing to bump, so it goes inside. So okay, so then I get 3, 3, 3, and now I have to insert the top element, which is 2, to preserve the shape. So this is 3, 1. Right now okay, so now I'm going to insert this 2. Now the largest element smaller than this is the 1, so I get 3, 2, 1. And now the 2 goes here. There's nothing strictly smaller than the 2, so it goes to 2. And now I preserve the shape 2, and I add a 2. Top entry is also 2 coincidentally, so the shape is 3, 2. Now I insert the 1.
Sir?
Yes?
The thing in the top row that got bumped was 1, right?
Where?
In the last stage, in the 5th step, while in the first row,
sorry,
we bumped the 1 with 2.
That's right. Yes, so this is wrong. Yes. Thank you. So I bumped the 2 here. I bumped 1 here with the 2, so it entered, and the 1 is now going to bump. Yeah, so I made a mistake there. Thanks. So this is 2, 1. Yeah, good. And now I'm going to insert the 1. So now there's nothing to do. In the sense that there's nothing smaller than 1 in the first row. So I get 3, 2, 1, 1. And now I preserve the shape, so I add a 2. So 3, 3, 3, 2, 2, 2. And my shape is 4, 2. Sorry, this should be 2. Okay, good so far. Let me minimize a little more. Okay, so now I'm going to insert the 4. Okay, so now everything is smaller than a 4, so the 4 bumps the 3, so I get 4, 2, 1, 1 in the first row. Now the 3 is going to do some bumping, and everything is smaller than the 3, so the 3 enters here, and now the 2 goes in the last row, or whatever, creates a new row. And here I want to keep everything the same, 3, 3, 3, 2, 2, 2, and now I want to enter the top fellow, so that's a 1. And so my shape is now 4, 2, 1. Let me try to squeeze it in here. So 8. Okay. So now let's do it carefully. Again, I insert the 4. Now the 4 bumps this 2, so I get 4, 4, 1, 1. Right smaller. Now this 2 which got bumped will bump this 1, so I'll get 3, 2, and now the 1 is going to sit at the bottom. So it's 2. And then I have 3, 3, 3, 2, 2, 2, 1, and now I have to add this 1. And the last stage I'll fit it in over here. So what am I going to insert? I'm going to insert the 2. So the 2 bumps this one now. So it's 4, 4, 2, 1. And now the 1 just goes in subsequent. So I get 3, 2, 1. And so 3, 3, 3, 2, 2, 2. And now I add this one over here to maintain the same shape. And so, oh, sorry, I forgot to write the shape here. This was 4, 2, 2. And now this is 4, 3. U. Okay. Any questions about this? I'll wait a minute. Let's see. Okay. Good. So let's go back here. Okay. So, so of course, this algorithm would not be of much use if it were not a bijection, and it turns out that it is. So, so again, I'm skipping some steps. So here it's a little more tricky to prove because one has to be careful about the equality of entries and so on. So by the same inverse bumping procedure, and noting that equal entries of Q, this is kind of the crucial point, are inserted from left to right. This requires a proof, but I'm not getting into it. We can show the following. You see, earlier, okay, let me write the level. Or maybe let's just go through the. So suppose I wanted to do the inverse algorithm. So let's compare with the RSK, with the usual RSK. So I look at Q and I see which is the largest entry. That was the entry that was inserted last, and I go back up and I constructed the last element of the permutation, pi n, and then I go backwards there, right? Here the problem is that you can see it already here. We know that our two-line arrays have the property that the top row is weakly decreasing, so I know that I have to look at the 1. But now to apply my inverse insertion procedure, which one should I start from? You know, this is not obvious at all. So one can show, so this is the point that I was mentioning, this is a kind of lemma that one has to show that if you have an entry, if you have same entries, then they are inserted left to right, not necessarily in the same column. So if you check, you will see that the ones, this one is inserted first, then this 2 is inserted first, and so on, for everything. Okay, that's the point. So then so you see it's a little more complicated to prove the following. So the correspondence A via Rsk prime to PQ is a bijection from the set of R cross S matrices of non-negative integers to the set of pairs of column strict plane partitions of the same shape such that the largest part of P is at most S and the largest part of Q is at most R. This should be small s. Okay, so I mean, if you go back to this construction, you see that the UIs are the row entry, I mean row indices, capture row indices, and the VIs capture column indices. So if it's R, the UIs, maximum entry among the UIs should be R, which is of course the maximum entry of Q, not of P. Okay, so this gives us this nice bijection. And has anybody seen already why we need column strict condition in this in partition? I mean, in the sense that you will only get column strict plane partitions, you will not get all plane partitions. You cannot have two entries equal below, and this is related to this thing that I told you of bumping being of entries strictly small. Okay. So now we have most of the ingredients required, or let's say 70% of the ingredients. So required to prove our theorem. So we now want to construct a single plane partition, okay, from a pair of cells. Course. Okay, so let's go now. So first, I want to show you how to do it for how to combine two strict partitions. So first, or if you like, one row. Combine two distinct partitions. Remember, a distinct partition is a partition with distinct parts. These are also called strict partitions. Okay. So suppose lambda and mu are partitions. I don't care of what size. Strict partitions. Such that L of lambda equals L of p, where L of lambda equals number of, is the length of lambda, is the number of non-zero parts. I don't know if I defined it. Just listen. I'll define it. Okay. Okay. So now suppose you have two such partitions. And we are going to construct a regular partition without any constraints on this. So for a strict partition, definition for a strict partition lambda, the strict shape or shifted Ferrer's diagram, shifted diagram, it's a Young diagram, is obtained by left justifying the rows in a staircase shape. Just like for descending plane partition. So let's do an example. So let's say lambda is 532. This is a strict partition with 3 parts. Change the background. So I'll draw 5 over here. Then I'll draw 3. If I were to draw a regular partition, I would put the 3 there. But what I will do instead is shift. It's in a staircase. And this is 2. Okay, so this is the staircase shape, and because it's strict, if I look at it from the right, it looks like a Young diagram. I mean, I will never have overlaps. I'll never have overhangs on the right hand side. That's precisely because this is okay. There can be equality, but that's okay. So that's what a strict shape is. Now, so remember. Maybe it's better to do this. Okay, so now I'm going to tell you how to construct this thing. So suppose lambda and mu are strict partitions with the same length. This is important. Form a new partition, regular partition, row, which is row of lambda comma mu. The order is important. By merging the strict shape of lambda and the conjugate of that of mu along the diagonal. So the conjugate of this is obtained by reflecting this strict shape about the diagonal. So it's better to do an example. Otherwise it gets confusing. So and this is why it's important to have both of the same shape. So let me take the same lambda and let me take mu to be 6, 3. Again, they have 3 parts. Okay, so what I'm going to do now is, so I have my 531 from before, so that is 532 from before. So what I'm going to do is I'm going to construct 631 this way, where the so this is 6, you see, and this is 3, and this is 1, and it's already included. So no. Where they merge along the diagonal. So this is 5, 3, 2, and this is 6, 3, 1. And you merge them over there, you sort of staple them exactly on the diagonal. Okay? And now you see you get a good old partition of the usual form. So here is an exercise for you. So I'll give it in the next homework. The map lambda mu to row lambda mu is a bijection. So this is row is a bijection between pairs of strict partitions with k parts and partitions with what is called the rank k. So what's the rank? Where the rank is the largest j such that partitions largest such row j is greater than. So here row is so 5, 4, 4, 2, 1. So you look at let's see. So is row 1 greater than or equal to 1? Yes. Row 2 greater than or equal to 2? Yes. Row 3 greater than or equal to 3? Yes. But row 4 is 2, which is strictly less than. So another way of saying this is that it's the largest square starting at the 1, 1 cell which fits inside row. So this 3 by 3 square fits inside row. That's called the Duffy square. Okay, so these are some names. So that's another way of saying it. Okay. So then size of row as a partition is the size of lambda plus the size of mu minus the length of lambda, which is also the rank of row. Okay. So that's why the lengths have to be equal, so that we can staple them together. Okay, so fine. So this was a way of merging two strict partitions to get a new partition. Now we want to extend this to CoSPPs. That's column stacking. So now given CoSPPs P and Q of the same shape, so if they are the same shape, the ith row and of P and the ith row of Q have the same length, and that's what is going to, and each of them is a partition. So that's what is going to come. So now given P CoSPP is the same shape, apply row to each column of P and Q. These are strict. Remember, so they are column strict. So each column, like in this example over here, each column is strict, right? So, and each column is a partition of the, and because they have the same shape, each column has the same. I mean, the ith column of P is the same. Okay, so to form columns U of a plane partition, pi. Okay, so going back to our running example, we had P was 4421, 3112. Oh no, this is not a running. Oh, sorry, this is another. So this is, and let's say Q is 5322, 421 and 1. And now I will construct pi by merging. Okay, so we merge 432 and 541, and oh, by the way, here's a good programming assignment. So exercise: write a program to implement row. Okay. So it should take as input two strict partitions, and it should give you this one. So right. Okay. So here, so okay, if I had more time, I could have written this program and check. So okay. So let me tell you the answer, and maybe we can check. No, we can't check. So, so I claim that row of 432541 is 44422. Row of 4132 is 422. Row of 21 and 21 is 22, and row of 1 1 is this one. Oh, sorry, 1 2 is no, is 1 1, because this is going to be. So we are going to get 4 4 4 2 2 4 2 2 2 2 1. Okay.
Excuse me, sir.
Yes.
In the first merge that you did, shouldn't there be a 5? Because one of you're merging a 541 with something, so.
No, but this is the column length. Here, right? You're talking about this one, right?
Yeah, my mistake, sorry.
But this is the column. So the check of that is that this has 5 columns. I mean, this has 5 rows. Sorry. So because Q goes down 6. So here you would have had a 5. So you will have 5 rows in row. Okay. No pun intended. Okay. So it is kind of clear, if you believe this exercise, that each column is weakly decreasing because it's a partition. What is not immediate is that the rows are weakly decreasing of pi. Right? So I'll ask you to check that. I mean, pi is also a plane partition. and of course the column strict condition is not. Okay, so what we are doing is, I mean, somehow the fact that P and Q separately satisfy the condition of being a plane partition along rows ensures this. So one has to check it a little carefully. So what we have to do is to show that any entry of pi is less than or equal to the entry to the left of it. It's of course greater than, is less than or equal to the entry above it by construction. I mean, not construction, by this exercise. Okay. Okay, one last step. So given a plane partition pi, replace the ith row of pi, which is itself a partition, by its conjugate. For all I, to obtain a new partition, a new plane partition, which we'll call pi prime, which is pi prime of P and Q. So we started with P and Q, and now we are going to do this procedure. So here, let me do it over here. So pi prime is equal to what? So I'll take the conjugate of each row. Okay, so 4, 4, 2, 1 will give me 4, 3, 3, 2. So I've done this already, so that's why I can do it faster. I'll leave it for you to check. 4, 2 gives me 2, 2, 1, 1. 2 gives me 1, 1, and this 2 also gives me 1. Okay, and it's easy to see, assuming that pi is a plane partition, that pi prime is also. Okay. Okay, so now we need some statistics for these guys. Okay, so we are going to need to compare various statistics of the column strict plane partitions with that of pi. So for with this plane partition pi prime. So for a column strict plane partition P, let mod P be the sum of Pij. Actually, for any plane partition, this I want this. Okay, no, I can put mu P be the number of parts of P, and max P be the maximum entry among the Pij's, which is of course P11. And for a plane partition pi, let mod pi be the sum over Pij's. Col pi be the number of columns of pi, and row pi be the number of rows of pi. Okay, so I note that max of P is the same as max of pi, which is the same as col of pi prime. y is max of p. So you take max of p, which is the 1/1th entry. This is also going to be the 1/1th entry of pi, right? And because you're going from pi to pi prime, you take the conjugate. This is going to be the number of. This is going to be. This is a coincidence here, but in general, this will become the number of columns of pi prime. It will become the length of the first row of pi prime, which is the number of columns. And max of q is row of pi, which is also row. So row of pi. So this is related to this confusion that was there earlier. Max of q is going to be the length of the first column, which is also the number of rows. And of course, on taking conjugation row-wise, you don't change the number of rows. So the number of rows of pi is the same as the number of rows. And lastly, the size of p plus the size of q minus nu of p is the size of pi, which is also the size of p. So remember this merging, for this merging we had the size of the partition given in this way, and each single entry contributes to the diagonal in this merging. So you have to subtract by the number of parts to get the size. So this nu p is also of course nu. Okay. Okay, so now I can prove the theorem. So let PPRS of n be the number of plane partitions of n with at most r rows and s columns. Okay. Then sum n greater than or equal to 0, PPRS of n, also q to the n, is the product I equals 1 to r, j equals 1 to s, 1 by 1 minus q to the I plus j minus 1. Okay, so again, very nice generating function formula, and notice there's no problem with the denominator because this power is at least 1. Okay, so we have all the ingredients to complete the proof, and that's why we needed all these statistics. So the key point is that the generating function for R by S matrices with non-negative integer entries is easy. And this Rsk prime bijection is going to give this correspondence. So start with A and R by S matrix, integer R by S matrix. Entries in non-negative integers, use the Rsk prime correspondence by and this the previous bijection this one. So I think I stated it somewhere. Okay, never mind. To obtain a plane partition, pi of A, which is pi prime of PQ. Okay. Now every column in the two-line representation of A, every column J occurs Aij times, of course, I said that earlier, and inserts J in P and I in Q, right? So, so you have Aij insertions of J in P and Aij insertions of I in Q. So that tells you that the size of P is the sum over all Ij of Aij times J, and the max of P is the max over all J such that Aij is not equal to 0, right? If you are going to have a 0 column at the end, that's not going to matter. That's not going to make any difference. And similarly, size of Q is the sum over Ij of Aij times I, and max of Q is of course the max over all I such that Aij is not equal to 0. So again, if you have an empty row at the bottom, it doesn't count. Okay. So then, what is the size of pi of A? This we already said is the size of P plus the size of Q minus mu of P. Okay, so what is the size of P plus the size of Q? So, so I sum over all Ij. I have this Aij, and then I have I plus J, and each Aij over here counts once when you count the number of ones. So it's minus 1 over here. Okay. So I'm out of time. Give me 2 minutes and I'll finish it. Okay, so we are almost done with all the ingredients. So then, what do we have? So let's look at the left hand side. So n greater than or equal to 0, PPRS of n, Q to the n. This is what we have. So now, this is by definition the sum over all pi a plane partition. Row of pi is less than or equal to R, call of pi is less than or equal to S of Q to the mod pi. Right? This is by definition. And now by this correspondence that I just said earlier, I'm going to write it as a new sum. So this is a sum over A and R by S n matrix of non-negative integers, Q to the what? So here mod of pi becomes this. So this is Q to the sum over Ij. Well, of course, if you want, let me be a little pedantic. So I goes from 1 to R, J goes from 1 to S. I'm writing the same thing, I'm just writing it more systematically. A, I, J, I plus J minus 1. So this is what I have to sum for every such matrix. Now Q to the sum of something is the product of the corresponding Qs. And this, there's no restriction on Aij. Right? So the Aij's run over all possibilities. So I interchange this sum which will become a product with this sum. So I'll have product I equals 1 to R, product j equals 1 to S, and now I'll have for each ij, I'll have this variable aij which will be greater than or equal to 0, and I'll have q to the aij times I plus j minus 1. Okay, but what is this? This is precisely aij is just some dummy variable. Call it alpha or something. I and j are fixed, right? So this is just a geometric series, and this gives me 1 by 1 minus q to the I plus j minus 1. Okay, which is the right answer. Right, so that's what I had. Okay, so I have still not managed to prove the thing I promised, but it's going to fall out as a corollary pretty quickly. But maybe I shouldn't talk about it now. So, are there any questions? Or I can stop recording. Any questions about the proof? Okay, so let me stop recording.